Shalom lekulam! In the previous episode we discussed ways to make the programs faster using nothing but a single CPU core. Now we will pick up from where we left and take the vanilla Mandelbrot fractal renderer and make it faster with multiple CPU cores. As you are probably well aware, modern CPUs are designed to have multiple CPU cores. For example, here's a photograph of an AMD Ryzen 7 CPU die. Each core can execute different instructions and in fact run different programs simultaneously. This is in contrast to SIMD, where a single core executes a single instruction but applies it simultaneously to multiple data. You can of course use SIMD and multiple cores simultaneously. Doing so would effectively multiply the SIMD benefits by the number of cores. Now if you look at the picture, you notice that this processor has 8 cores, but according to AMD specifications, the processor can actually run 16 threads simultaneously. This is called hyperthreading. How does it work? Let's study the individual core for a moment. These are the components of an individual AMD Zen core. During normal operation of the CPU, not all parts are utilized at 100% continuously. A component such as ALU might be waiting for data from the load and store unit, or there are no floating point instructions in the pipeline, meaning the FPU has no chance but to idle and so on. Hyperthreading attempts to better utilize these resources within a single CPU. Now there are caveats like with SIMD. Calculating the benefit from running a program on multiple cores is not trivial. If your program needs to access the memory, all the requests to read or write must be funneled through the same RAM I/O interface. With hyperthreading, 2 threads are competing for the same shared resources within the CPU core. And if the threads do write to the RAM, there are all sorts of cache coherency issues that will cause the cores to wait until data is synchronized between different caches. For that topic I recommend the excellent article series called What Every Programmer Should Know About Memory by Ulrich Pepper. The link can be found in the video description. And there's also the mutual exclusion stuff, which I have explained in the C++14 thread tutorial video. But the bottom line is that, like with SIMD, performance does not necessarily increase at the same rate as the number of threads. It may even decrease. It really depends on the situation. Now, by far the simplest way to add threads to your program is with OpenMP. Watch this! There, done. I have an article on my website that explains OpenMP in very deep detail. The link is in the video description. But for the sake of introduction, let's review quickly what happened on that line. The OpenMP pragma is a very concise way of adding parallelism to your program without changing its semantics. First, the word parallel instructs the OpenMP system library to generate a team of threads. Then the word for causes the following for loop to be divided across the team of threads, so that each loop iteration is run exactly once, but multiple iterations may run concurrently. The clause schedule controls how exactly the iterations are assigned to each thread. The word dynamic answers that question. In the dynamic schedule, each thread processes a single loop iteration and then chooses the next available one. This can cause a research congestion where all threads pull a shared variable, but it works well for Mandelbrot rendering, where every row takes a long time to calculate. The reduction clause instructs the compiler to generate special code where every thread gets a private copy of the specified variables, and once the thread is done, the result is merged into the actual variable by that name. This approach is called reducing. The term should be familiar to people who deal with functional programming. Here the n inside variable is reduced by calculating the sum of the private copies of the n inside variable. The goal in OpenMP is to write such pragmas that the code will compile and work just fine even if the compiler ignores the pragma. Nearly all compilers understand OpenMP, but usually you have to enable it explicitly. For example, in GCC and Clang you have to specify FOpenMP, or the compiler will ignore your pragmas. But like I said, you can find very detailed information about OpenMP on my website. Check the link in the video description. Now, this program is exactly like the vanilla program, except for the single OpenMP directive that I just added. There is no SIMD in this version. Let's see how it runs. It is about 7 times faster than the vanilla version when run on my quad-core i3-1281v3 with hyperthreading. Not bad for a single line of code. In the previous episode I mentioned Intel Cilk Plus. I included it in this video because GCC supports it out from the box. Cilk Plus extends C++ with 3 keywords. The first 2 listed keywords deal with asynchronous functions, and the third one is for applying threads into a for loop, just like in OpenMP. But in OpenMP there was also this reduction clause. Is there something equivalent in Cilk Plus? Yes and no. Cilk Plus comes with a large template library which defines various reducers to use with thread programming. Here is an example how to use the add reducer. It is somewhat invasive to the program. The same code will definitely not compile without Cilk Plus support. But you do what you must. And this is the performance graph. It is somewhat slower than the OpenMP solution. This is because Cilk Plus defines a particular work sharing algorithm that just happens not to be optimal for this application. There is also considerable jitter. I'm not sure, but I suspect that the Cilk Plus library is creating and destroying new threads continuously rather than using a pool of threads like OpenMP does. Or the problem is in the mutex actions in the reducer. In any case, it ends up slower than OpenMP. Intel also has a different thread library called Thread Building Blocks, or TBB for short. But because it is just a library and it is neither part of the C++ standard nor is it supplied with my compiler, I will not cover it in this video. Besides, the standard C++ already has threads. I have made a video about C++ 14 threads in the past, so let's jump straight to the code. I don't actually know what is the recommended way to determine the optimal number of threads to run, but I hard-coded the numbers 8 here because my CPU has 4 cores and hyperthreading. The for loop scheduling and the reduction algorithm are exactly the same here as with OpenMP earlier. And now when we run the program, we see the performance is also exactly the same as with the OpenMP version. Conclusion. Your CPU has multiple cores and it is wise to utilize them, because it is unlikely that clock speeds will significantly increase anymore. It may not always be possible to use threads, but even when it is possible, it might not necessarily help. Threads and SIMD are not mutually exclusive. In the first episode we only dealt with SIMD and ignored threads. In this episode we only dealt with threads and ignored SIMD. In the next and final episode we will bring yet another technique into the mix and see what happens when we combine all 3 methods. I am Bisqwit and I wish you shalom in all areas of your life. But before the video fades out, there is something else I wish to say. This series has been made possible by the support of some very particular people. Westmeal, Vincent Hamilton, Justin O'Connor, David Lax, Cordite, Connor Olding, Peter Cooper, Colin Mills, Joe Zumansky, Nate Vivod, P.I. Mitchell Taylor, Adrian Papari, Brandon Belfry, Adam Ewing, Bernard David Nguyen, Psychonics Christopher Jones Rutfullu, Greg Pufflord, Sebastian Moren, Gustav Louv, Piotr Michniewski, Megna Young, Tom Marty, Sven Almgren, Andrei Popa, Mike Mayer, Jens Bilzom Aiken, Bruce Lanham, Valacek, John Mayo, Radek, Riku Rajaniemi, Joshua Dinardo, Mike Alexander Simruat, Nicolas Londi, Dioxilai, Andreas Wiffler, Tom Hodder, Co-Colonel, Andrew Vage Sorensen, Andrew Niceherd, Henrik Gemignani, Sergio Gonzalez, Andrew Anderson, Arne Wieding, Ed Baker, Simon Wacker, Keloran, David Streeter, Joao Asunjao, Atski, Zebdeos TV4 Elp, Joshua Vicioso, BJ, Alex T. Jensen, Gabriel Garcia, Ben Grass, Darko Mecharos, Jose Victor Ramos Sanchez, Patrick Karamer, Cassandra Mish, Ryan Emmanuel Deminian Terentev, Tongol Quaixor, Hawkins, Maxwell Kepler, Adrian Siekierko, Kamil Dabrowski, Dam Amlund Thomsen, Hrnek, Bezucha, Tuomas Hyvönen, Ryan Young, Jacob Schaffer, Alessandro Gatti, Mike Tehan, Benjamin Clegg, Kalle Siukola, William Finbeer, Alexander Bachler, Jan Sol, Balais Saunders, Ron Hockman, Markus Therkildsen, Sebastian Stabinger, Georges Duperon, Stepan Usatiuk, Mike Warren, Pampi Vigre, Philip Hafner, Sounds God, Sean Phillips, Alex Jansi, Geldo Silva, Andrew Dinihan, and Prographer. You have responded to my Patreon campaign or have contributed on PayPal. You guys are really kind. Huge thanks to also anyone who shares these videos on Twitter, Facebook or other social media. If you wish to join this list, please follow the links in the video description. Thank you for watching and have a most satisfying and fulfilling day. It may not always be possible to use threads, and even when it is possible, it might not necessarily help. I am Bisqwit, and I wish you shalom into all areas of your life.